So you like fractions, you like algebra. Now we bring those two glorious things together and we're looking into algebraic fractions. We're going to talk about some of the key methods for combining algebraic fractions, and then we're going to do a little bit of a precursor to the next level on, which is finding a way to split up an algebraic fraction into simpler ones. To start with, I want you to have a go at these. Each one involves either addition, subtraction, multiplication, or division, but the crucial difference is we've got algebraic terms instead of numbers. You could argue that in some sense this makes things easier because you're not hunting for a common factor for 480 and 7,200, but in some ways it's going to be more confusing, or it might bring up some misconceptions. So I'd highly recommend you pause and you work through each of these. You do your best to come up with a simpler way of writing each one if you can, and if you can't, then see if you can convince yourself that it's written as simply as it can be. When you're ready, we'll go through some answers. So for the first one, when we have two fractions that are multiplied, it doesn't matter what the numerators and denominators are for each one. We simply multiply the two numerators and we multiply the two denominators. A good way to make sense of this numerically is to think of something like half of a third. If you have half of a third, then of course you have a sixth, because you have 6 of those pieces in one whole one. But that means that you've got a 1 over 2 multiplied by 1 over 3, and you've ended up with 1 over 6. Another way to think of this would be if you multiply by a third, it's equivalent to dividing by 3. So the number gets smaller by a factor of 3 times. Now, the bigger the denominator, the smaller the size of the number. So if we want to multiply by a fraction, we use the numerator of the fraction to make our original fraction bigger, and we use the denominator of our fraction to make our original fraction smaller. For the next one, it looks similar, but this time we're adding the fractions, and it's important to notice here that addition with fractions is not as simple as multiplication, and that's because fractions are basically built out of multiplication. A fraction is essentially a division, the top divided by the bottom, and division is the inverse operation of multiplication. When it comes to addition, though, things are a little messier, and that's because the fractions are different types, a over x and b over y. Think of it like a half plus a third. There's no easy way of comparing those two fractions because they're different types. And the only sensible approach is to turn them into fractions that are the same type. The same type is another way of saying the same denominator. Like denominations of coins will be types of coin or sizes of coin. We don't want to work with halves and thirds. We'd be more comfortable dealing with sixths. So we think of a half as being 3/6. We think of a third as being 2/6. And then they're easy to compare, they're easy to add, subtract, etc. So with this one, the best way is to multiply the top and the bottom of the first fraction by y, and multiply the top and the bottom of the second fraction by x. Now, I want you to notice the phrase I used there. I didn't just say multiply the first fraction by y. If we want to multiply that first fraction by y, we could, but it will give me a bigger fraction. It will be y times bigger. ay over x is actually what it would be. If I multiply the top and the bottom by y, then mathematically speaking, all I'm doing is multiplying by y over y. I'm just multiplying by 1, and that's why it doesn't change the value. It gives me a different way of writing the same fraction. That's why 3/10 is the same as 6/20. Not the same as 6/10, but it's the same as 6/20. By doubling the top and the bottom, you've kept the ratio between the numbers the same, and therefore the fraction is equivalent. It has an equal value. Now, once the denominators are the same, it's like adding currencies. You can't easily add pounds and dollars, but if you convert your pounds and your dollars both into euros, you could add the number of euros because it's the same type, the same denomination, the same denominator in this case. So we have ay over xy and bx over xy. We can add them together and get ay plus bx all over xy. The next one, x add 4y squared over x add 3y. If you are looking to simplify or cancel things down, one of the common mistakes people make is to attempt to cancel the x's. They say there's an x on the top, there's an x on the bottom, so I'm going to cancel the x's. The danger with that phrase is that cancel is not a thing that happens in maths except under specific circumstances. If I have 37 plus x minus x, I could cancel the x's because they essentially reverse one another in effect. If I was multiplying by x and then dividing by x, then x becomes irrelevant because, again, the effect is reversed. When we cancel things, it's because mathematically they reverse one another's effect. And in a fraction sense, generally speaking, what that means is we divide the top and the bottom of the entire fraction by the same thing. And x is not a factor of the entire numerator. It's not a factor of the entire denominator either. X add 4y squared cannot easily be factorized, and neither can x add 3y. In fact, the only algebraic factor of x add 3y is x add 3y. So that one is going to stay exactly as it is. Now, moving on to the division. The thing to remember about division is that it's the inverse of multiplication. If you divide by 2, it's the same as finding half of something. So half of or half times something is equivalent to getting that something and dividing it by 2. That's because 2 and a half are reciprocals. One of them is 1 over the other one. And in this case, we can use that idea. If you want to divide by b over y, then that's equivalent to multiplying by y over b. And as soon as you recognize that you can change a fraction around, multiply by its reciprocal instead of dividing by the original, then you can divide fractions as easily as you can multiply them. I should point out that you'll very, very rarely have a division sign in an algebraic expression. What you're more likely to see is just a fraction within a fraction. And you might find it helpful to break it apart and call it division. You might also find it helpful just to multiply the top and the bottom of the entire fraction by whatever pesky number appears in the denominators. But you'll see examples of that later on. For the next one, we're trying to do a subtraction, so we need to take into account the methods that we were using for addition. We need a common denominator. But last time we had x and y, so we had a common denominator of xy. This time we have xy cubed and x squared y. And what I'm going to use is the lowest common denominator. Instead of naively multiplying the two denominators together, I'm going to say what's the smallest collection of x's and y's that xy cubed is a factor of, but x squared y is also a factor of. Well, 1x would not be enough because we need x squared for the second fraction. But x squared would be enough because that's more than enough for the first fraction and it's just enough for the second fraction. We can do a similar thing with the y's, so our common denominator is going to be x squared y cubed. And as soon as we've converted our fractions, we multiply top and bottom of the first fraction by x, we multiply top and bottom of the second fraction by y squared. Now both fractions have a common denominator and they can be easily combined, ax minus by squared. The next one, you might think that just like the previous one on the bottom line, can't be simplified. There's no obvious factors, but just because there are no obvious factors doesn't necessarily mean there are no factors. In fact, if you look carefully at the top, we have a pattern called the difference of two squares. Difference refers to the subtract sign in the middle there, and the two squares we're looking at are x squared and, well, this one is 2y squared. If you square 2y, you get 4y squared. And anytime you see that pattern, it should remind you of these brackets, the a plus b times a minus b kind of format. X plus 2y multiplied by x minus 2y. If you try expanding these out, you'll see x times x, there's the x squared. 2y times minus 2y, there's the minus 4y squared. And then there's the middle terms, the 2y times x, and the x times minus 2y. And because those two are the same size but the opposite sign, they cancel out and the middle terms completely disappear. We're left with just the x squared and the minus 4y squared. And the great thing about that is that that fraction happens to match, the brackets in the numerator have a matching bracket in the denominator. X add 2y is a factor of the top and a factor of the bottom. So that can now cancel out. We're essentially dividing the entire numerator of the fraction by x add 2y and simultaneously dividing the denominator of the fraction by x add 2y. So you could argue that on the bottom we now have the number 1. But of course, if we have a denominator of 1, we typically don't treat it as a fraction. We just leave that bit out. Next, we're going to look at an example together. This one looks more complicated, but it's a good example to work through because we can see how the same standard set of steps will help us to get through any messy looking algebraic problem. The first thing we do is we factorize. Factorize anything you can see that isn't yet factorized. Factorize the numerator and the denominator of any fractions involved because we're going to want to know what the factors of each one are. Well, there's a quadratic on the bottom of the second fraction, so I'm going to factorize that. It comes to y plus 1 times y plus 3. If you have a more complicated looking quadratic and you think it's going to take you a while to factorize, remember the calculator can tell you the roots of any quadratic. You just have to be a little bit careful interpreting the roots because they don't necessarily tell you exactly what the factors are. They just tell you what the solutions would be if you said equals 0. In other words, if we had 2y squared, add 8y, add 6, then the roots would still be -1 and -3, but we'd have to include a 2 in addition to the two factors y add 1 and y add 3. Anyway, now we've got our factorized fractions. The next step we're going to use is taking advantage of the fact that division is equivalent to multiplying by the reciprocal. So we're going to change the divide sign to a multiply, and we're going to flip the second fraction over because instead of dividing by the original fraction, we're going to multiply by its reciprocal. The next thing we do is we use the fact that we can multiply fractions simply by multiplying their numerators and multiplying their denominators. So all of the numerators are now just written next to each other because that's how we multiply in algebra, and it's the same with the two denominators on the bottom. And the final step is to do any simplifying that can be done. So in this case, we look carefully at the top and the bottom, and hopefully you'll spot there is y plus 3, a factor of the top and of the bottom. And also there's a y squared. The y on the top cancels with one of the two y's on the bottom effectively. So y squared is y times y. And that means we will end up with, on the top, just y plus 1, and on the bottom we have y. Y plus 1 over y. It's worth pointing out at this stage, if you simplify something algebraic, you might think there's no easy way to test your answer. It's not like an equation where you have a number as your solution, you can go back and check. But with any expression you've rearranged, if you want to check that you've done it right, a relatively quick method is to just pick a number. Try a number for y, put it in, see what you get. So if I decide that y can equal 2, then if I substitute that into my final expression, I'll get 2 plus 1 over 2. In other words, 3 over 2, 1.5. Now I could do the same thing at the top. 2 over 2 plus 3 divided by 2 squared over 2 squared plus 4 2's plus 3. It's not super quick, but it's relatively fast to do, especially on a calculator, and you can check to see if you get the same result. Now, just because you get the same result doesn't prove that the two things are always the same for any value of y, because potentially you've just got unlucky and you've picked one of the few values of y for which those happen to be the same. But more often than not, if you've made a mistake, they won't match because you've picked a random number, and if they don't match, you know you've made a mistake. If they do match, you're probably fine. It's unlikely that the two things are different and yet you've randomly picked a number for which they are the same. So if you need an algebraic reminder of the various rules that we use for fractions, you might want to copy these down. Hopefully they are ingrained in your head with a bit more permanence than just arbitrary formulae that you are trying to memorize. The idea behind multiplying and how division can turn into multiplication is important and fundamental. If you're dealing with addition or subtraction, we always need to find a common denominator. The next one I've put in, AK over BK equals AB, is essentially a reminder that if we can factorize the top and bottom and find a common factor, then we can simplify. And the last one is not often used, not often included in lists like this, but I think it's worthwhile because we often miss the fact if you multiply a fraction by itself, it means you're doing, say, A over B times A over B. Of course, you'll get A times A over B times B. But for some reason, it's less obvious to us that when you square a fraction, you square the top and the bottom. It works for cubing a fraction. It works for square rooting a fraction because that's essentially a power of a half. So that's quite a useful method to keep in mind. Now you should be able to have a go at the questions from exercise 1B in pure year 2.
The next example we're going to do involves adding fractions. So we start out with an expression that might look quite complicated on the surface, but remember, using our standard technique of factorizing complicated looking expressions, we can break them down and see what they're made of. So in this case, we can factorize the denominator of the right-hand fraction. We get y plus 1 times y plus 3. And when we do that, suddenly we can see that there is something in common with the denominator on the left. In fact, these two denominators have a common factor of y plus 3. And that means that we can do better than simply multiplying the denominators when it comes to adding these fractions. You'll notice on the right here, where we were adding fractions, we had a b and a d, and there was no information there about whether b or d shared any common factors. So we went with the standard approach. Let's just multiply them together. If we don't know of any common factors between the two numbers, let's say we're adding sevenths and thirds, well, it's a safe bet to use 20-onths. We multiply the 7 and the 3 together, and that will definitely be a common multiple of 7 and 3. Now, in this case, we can see that we've got a slightly more efficient thing we can do. It'd be a bit like adding halves and tenths together. You wouldn't need to turn them into 20ths. You could turn them both into tenths. And that's what we're going to do here. We're going to use the fact that y plus 3 times y plus 1 is a multiple of both denominators. So we multiply the left-hand fraction by y plus 1 over y plus 1. And it's important here to remember, essentially, this is just a fancy way of multiplying by 1. We're multiplying by the same thing on the top and the bottom of the fraction. Once we've done that, we can safely add the numerators. Remember, we can only add things together if they're the same type. That's why we can simplify 3x add 2x, but we can't simplify 3x add 2y. We can combine £3 and £2 to get £5. We could combine $3 and $2 to get $5. We can't easily combine $3 and £2. Until we're dealing with things that are the same type, we can't easily combine them. As soon as they are the same type, they combine really sensibly. So we have y times y plus 1, lots of 1y plus 3y plus 1, if you like. That type of fraction is 1 over y plus 3, y plus 1. And the numerator tells me the number, in other words, how many of that fraction I have. On the right, we have y squared as the numerator. When we add those together, this is what we get. Now, it's very tempting at this point to cancel out the y plus 1 bracket. It might be worth thinking for a moment, maybe pause and ask yourself whether or not that would be a correct thing to do, and if so, why, and if not, why not? But it's tempting because it seems to appear as a factor on the top and as a factor on the bottom. But the subtle distinction here is that it is not a factor of the entire numerator. It's a factor of that first bit, y times y plus 1. But then we've got this add y squared kicking around. And y plus 1 is not a factor of the entire numerator. When we look at something like this, ak over bk equals ab, we can simplify that because we're dividing the entire numerator and the entire denominator by k. With the fraction we're dealing with, there is nothing on the top that we can see that is a factor of the top, but also a factor of the bottom. In order to convince ourselves that this is in its simplest form, we would have to go a little bit further. So if there are some elements of your numerator that have still got brackets involved, we'd need to get rid of those brackets in order to effectively recombine things. Perhaps after we've expanded it, we can see a way of factorizing the numerator, and then if there is any simplifying that can be done, we will see it. Now in this case, if we do y times y plus 1, we get y squared plus y. Now we also have another y squared, so now we have 2y squared plus y, and you can pull out y as a common factor, y times 2y plus 1. Now you might have noticed you could also pull out y as a common factor without expanding that bracket. If you spot that it's y times y plus 1, add y times y, that's the same as y times 2y's plus 1. But once we've done that, it's now clear that this fraction cannot be simplified. We've got a perfect factorization of the top and the bottom, and none of those are the same thing. So we must be finished. And in general, when we're dealing with a fraction problem like this, there's often going to be some simplifying or cancelling out that can happen, so it's worth looking out for it, and it's worth always factorizing fully at the end as well as at the beginning to make sure if there are any common factors we can cancel them out. But if there aren't, then don't do it. And just like before, if you're not sure if a particular step is valid, just try putting a number in instead of your variable. We replace y with some value, preferably not 1 or 0, because lots of things simplify a lot if you put a number like 1 or 0 into them. But try putting some other number in instead of y. See what you get for the unsimplified expression, see what you get for the simplified one, and if they don't match, then something in your simplifying step must have been wrong, because there should be no difference between the results you get if all you're writing is a different form of the same fraction. You should be able to try some questions from exercise 1C now. I recommend you try a couple from near the beginning to get your eye in, and then when you're feeling more comfortable, focus on the exam style questions and the problem solving questions towards the end. Next, we're going to look at how algebra can help us to describe and generalize a pattern that we might notice with numbers. This is commonly where algebra will appear within a more natural context. We notice a pattern, it seems to work for a few special cases, for particular values, for instance, and we try to use algebra to describe the patterns involved, and then we perhaps see if we can prove that that pattern, that underlying structure, isn't just a fluke of the handful of examples we've tried, but perhaps it's something fundamental about the structure behind those examples. What I'd like you to do with the questions that are about to show up is calculate the value, but do it by hand. So don't use a calculator. We want you to think about the method you're using, because that will help you when you start to look at the more general case with algebra, which of course you can't do directly on a calculator. So I'd like you to try working out the value of each of these three, and then as you work them out, I want you thinking actively about these questions. What do you notice about your answers compared to the questions, or about the structure of the questions themselves? Why does this happen? Whatever you think you've spotted, can you come up with a justification? What intuitively, or in however you are able to describe it, see if you can describe what's going on. And then, will it always work? Do you think that the pattern you've spotted is something that you could generalize and come up with a general formula or rule for? So pause at this point, have a go at those, answer the three questions, and then unpause, and we'll continue. Right, you should have 1 over 20 for the first one. If you turn these both into fractions over a common denominator, the lowest common denominator you're going to find is 20. 4 and 5 are right next to each other, so they're not going to share any common factors. The jump between them is too small for them to both divide by 2 or 3 or 5 or anything else. So we need a common denominator which is actually 4 times 5. And when we do that, it means multiplying top and bottom of 1/4 by 5 and multiplying top and bottom of 1/5 by 4. And that gives us 5/20 minus 4/20. The next one's similar. We get 1 over 72. And the last one, again, 1 over 9,900. Now, hopefully you got the same answers as me. Hopefully you've noticed some interesting patterns within those. You might have noticed some completely different things to what I'm going to focus on, but one particular pattern within the questions is that the second fraction is always just a little bit smaller than the first. Both fractions are unit fractions. That means there's a 1 on the top, but also the second fraction is has a denominator which is just 1 greater than the denominator of the first fraction. That makes the second one slightly smaller, but only just. It is the next smallest unit fraction, if you like. The other thing that you've probably noticed is that the result of this subtraction is also a unit fraction. It's also a fraction that has a 1 on the top, and that seems to happen every time. And if you're curious about this pattern, you could try some more examples. You could even knock up a quick program in Python, or a spreadsheet will be the simplest, I think, just to calculate and see if this seems to work every time. Or we could think algebraically about the pattern that's going on. And that will also help us to investigate what's happening with the denominator, where the denominator appears to always be the product of the two original denominators. Let's think of it like this. If the first fraction is 1 over n, then the second fraction, the one we're subtracting, must be 1 over n plus 1. And it should be possible to combine these. I'd like you to pause at this point and combine those two fractions. You already know, hopefully, what kind of answer you're expecting, but see if you can calculate it directly from the algebraic fractions rather than just jumping to what you think the answer should be. When you've got it, come back and we'll see if it matches. Well, yes, it turns out if you put this together, you'll have n plus 1 over n times n plus 1 minus n over n times n plus 1. So the n's in the numerator cancel out. They cancel in the sense of you have an n and then you subtract an n. So the overall effect is that you don't have any at all at the end. You still have the 1 from the n plus 1, and therefore, yes, it appears that the pattern we noticed will always work. Not only for positive whole numbers, incidentally. Generally speaking, in algebra, when we use n, we are implicitly thinking of integers, often non-negative integers, often positive integers. And if it's important to make the distinction, then that should ideally be done as well. But if you use x, we're generally talking about any real number. So it could be positive, negative, it could be fractional, it could be irrational. There's no real limitation on that along the number line. But it turns out that this pattern that we notice algebraically here, it should also work for any other number. There's nothing that restricts us within the argument we followed to get this answer, which means if you try with some negatives, it should also work. As long as n is not 0 and n is not negative 1, you can think about why those two would break the pattern. But for pretty much anything else, you can test this out with 1 over root 2, take away 1 over root 2 plus 1, and it will give you 1 over root 2 times root 2 plus 1. It might look a bit different on the calculator because the calculator will probably try to rationalize that denominator for you, but test it out and you'll find that the two things always match. It's worth coming back at this point to the idea of algebraic and mathematical proof. This is something that you will have covered during your Year 1 course, and it's also something that comes up in the current chapter you're working on algebraic methods. We look at proof by contradiction. But as a bit of a precursor to what you're going to do on that, it's useful to think about what a proof is in maths. And a good, simple explanation of that is a fully justified explanation of why something is true. In other words, your proof will read like a convincing argument, step by step, where each step follows logically from the previous one, and the result is that it is undeniable, whatever the conclusion is you're trying to get to. Based on the assumptions that we agree at the beginning, your logical steps, your logical reasoning and processes cannot be faulted at any point, and the conclusion is the one that you were aiming for. Now we're going to see how that particular way of breaking apart a fraction could be used in a question like this. So we already know that we can use this pattern, 1 over x times x plus 1 is equal to 1 over x minus 1 over x plus 1. But I've turned it around this time. I've written it with the big complicated fraction on the left-hand side, and with the two simpler fractions, one subtracted from the other, on the right-hand side. And the reason for that is that we're actually going to use this sort of identity backwards. This is a little precursor to what's coming next, which is called partial fractions. And we'll talk a little bit more about that in the next couple of slides. But to start with, I want you to see how this result can help us to quickly calculate this big messy sum of 6 different fractions. So look closely at the fractions, see if you can identify what's special about them and how they might connect to the result above. I would highly encourage you to pause at this point and to think about it and see what the lazy method would be for calculating this sum by making use of the result that we have now managed to prove. Okay, hopefully, if you've had a bit of a think about this, you will have noticed that 6 is 3 times 2, 12 is 4 times 3, 20 is 5 times 4, 30 is 6 times 5. So each denominator is actually what we would call a pronic number or a rectangular number. It's kind of not quite a square, but it would look a lot like a square if you drew it out for most cases. It's a number multiplied by the one above. In other words, it perfectly matches the left-hand side of our identity, 1 over x times x plus 1. The only difference is the value of x for each one. So we have 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5 and so on. And our identity at the top allows us to rewrite every single one of those. We can do it like this. We know that 1 over 2 times 3 is the same as 1 over 2 minus 1 over 3. So we can write it out in that form. Can you see why that's going to be helpful? If you want to pause at this point and do a bit more working out so you can get to the answer before I do, then that would be great. Otherwise, we're going to continue. Look closely at the fractions we've got in our total sum. I've put them in brackets mostly just to make it convenient so that we can see which one links with which fraction. A third minus a quarter is a 12th, for instance. But now, if you ignore the brackets, because actually each bracket is just a single copy of each bracket added together, we can basically call it a half minus a third plus a third minus a quarter plus a quarter minus a fifth, and so on. And if you look closely, you'll see that the minus a third has a companion, plus a third, right next to it. And the same thing happens with minus a quarter and plus a quarter, minus a fifth plus a fifth, minus a sixth plus a sixth, minus a seventh plus a seventh. In fact, all of those middle terms will cancel out with each other, because every time a fraction appears like a fifth, there's another fraction just before, negative a fifth, that will cancel out with it and give us 0. And that means that all we need to do to calculate this entire sum is look at the very first term, which didn't cancel out because it was at the very beginning, and the very last term, which didn't cancel out because it was at the very end. And here we are. Half minus an eighth is a nice quick one to calculate, because a half is 4/8. There we go. You can see why this concept could also be used to deal with a sum that was much, much bigger than 6 terms. We could say I want to add up all the terms that are of this form, all the way up to the 100th term, let's say, or all the way to the 1 over 9,900, if you like, the one that we looked at before. And this pattern allows us to essentially, once we recognize what's going on, we don't even need to write out the middle terms. We just need to concentrate on how things cancel and then keep track of what goes on at the very beginning and the very end, known as like the edge cases, if you like. Now, it's worth mentioning, if you're planning to do further maths, this technique that we've made use of here is actually known as the method of differences, because we have a difference of two things, and as a result things will cancel out. And it's a really nice technique, and it's something that you will look at more if you do further maths. The next thing I want to talk about is specifically what it means to deal with partial fractions, and this is something you'll cover in more detail later, but the essence of it is working with a complicated fraction, like we had 1 over x times x plus 1, and finding a way to break it apart into simpler ones. Now, so far, we've not seen how to do that. We started with the simpler ones. We had 1 over x minus 1 over x plus 1, and we demonstrated that you could put them together to get the more complicated one. But just like with quadratics, where perhaps we first learn about them by expanding double brackets, and then when we're familiar with that, we can work through the inverse operation, factorizing, which is significantly more challenging and sometimes impossible for quadratics. We have a similar thing here. If we start with a complicated looking fraction, it's sometimes possible to break it apart into simpler ones. So we started with this, for instance. What about this fraction? 6 over x plus 1 times x minus 1. It's a different sort of pattern. It's now got a numerator that isn't 1. That's not something that's particularly crucial. What is important about this fraction is that it can be split up in a similar sort of way to the original one. And the trick with this is to make a guess at the general format that we're expecting. We use letters for any unknown values that are in there, and then we work backwards. Essentially, we are using the same technique we used to prove the original result. The only difference is, instead of knowing that there's a 1 on the top and a 1 on the top, we don't know what numbers are going to be on the top of each fraction. They may be the same, in some cases they may be different, sometimes they may be fractions, but if we know the kind of format we're expecting, we can confidently make this assumption. We can say that I think this fraction that has a factorized denominator with these 2 linear factors in the denominator, I reckon it should be splittable into these 2 fractions. So we've got a denominator of x plus 1, so we'll have a fraction with a denominator of x plus 1. But our denominator for the original fraction also had an x minus 1 factor, and that factor forms its own denominator over here. And then we work backwards. We start with the 2 separate fractions that can be added, and we add them. And it's a bit of a mess, but we're basically using the fact that the lowest common denominator is going to be the 2 denominators multiplied. So we'll have a times x minus 1 and b times x plus 1 added together. Now this looks complicated, but notice that the denominators now perfectly match. if x add 1, x minus 1 is the denominator on both sides of this identity, then in order to make the two sides perfectly equal for every value of x, we just need to make the numerators match. So we focus on this somewhat easier looking identity. 6 must be the same and must always be the same as a times x minus 1 add b times x plus 1. And the thing is, it needs to match for any and every value of x. That may seem like it makes it harder, but in fact it makes it easier. It means we're allowed to think of any value of x we like, and a and b must fit the resulting equation. So this is the little challenge I'm going to leave for you. Can you come up with values of a and b that make this identity true for any value of x? This last bit I want to talk about, little bonus section, is to give you a sense of the context of partial fractions. Within the A-level maths course, not just in further maths, but in A-level maths itself, we will revisit partial fractions a couple of different times. It turns out this general principle of taking a fraction which is complicated and breaking it into simpler pieces is quite useful. In the same way that factorizing is a helpful way of rewriting a quadratic, so we can solve equations, sketch graphs, we find that splitting a fraction into what are known as partial fractions, in other words, breaking that fraction apart into two pieces or more, is a convenient way of representing it for certain things that we might want to do with it. And just so that you've got a sense of the motivation behind this and where it's going, I'm going to give you a couple of brief examples. The first one is in binomial expansion. You will have covered binomial expansion already in the year 1 content, but the difference is you've only dealt with positive whole numbers for the powers. Now it turns out if we can break apart a fraction like this one into two simpler fractions, like these, then each of those could be written as a binomial. So the first one we can have x minus 1 to the power of negative 1, and of course the second one in this case also has a power of negative 1. And there is an equivalent binomial expansion formula that works for negative whole numbers, and it even works for fractions. So we can use it to deal with reciprocals of things, we can use it to deal with powers of brackets that might be related to roots, like a power of a half for a square root, or a power of 2/3 for the square of the cube root, and things like that. And it turns out if you apply that formula, you can construct a binomial expansion for x minus 1 to the power of negative 1, and you can construct a binomial expansion for x plus 1 to the power of negative 1. And if you can do that, then you can combine the two. Turns out this whole thing, when you put it together, you deal with the negative 1 and the take away positive 1, you have a negative x and you take away negative x. Some things cancel out, some things combine, and when you've done that, you get an overall expansion, which is now effectively equivalent to a binomial expansion, but it came from a fraction that was too complicated to write as a single binomial expansion. Breaking it into two has allowed us to deal with that. And the nitty-gritty detail behind how you get from here to here and how you get from here to here, that's something you'll cover once you learn binomial with rational powers. The next example is in integration. Integration is probably the biggest and meatiest and in some ways the most challenging topic in A-level maths. And there's so much going on and so many new things that you'll need to get your head around when you come across this, that you do not want to be stopping halfway through a process in order to make sense of partial fractions. It needs to be something that you're familiar with and comfortable with. So when you see, for instance, an integral like this, the integral of 2 over x minus 1 x plus 1, you can break that apart into separate terms, simpler terms. And although there is no easy way of integrating 2 over some quadratic, there is an easy way of integrating 1 over x minus 1 and 1 over x plus 1. Those simple things have some nice rules. They actually relate to the natural logarithm. So if you integrate 1 over x minus 1, you get ln of x minus 1. And if you integrate 1 over x plus 1, you get ln of x plus 1. And the reason for that, the detail, you will learn later, but the fact that it works allows you to integrate things that you otherwise couldn't.